now that we've covered basic probabilities, we want to look at something that's just slightly more complicated, just a tiny bit, and it's called the addition rule, and then we're going to talk about what complements are. So now we're going to be looking at more than one event happening. So if two events are disjoint, the definition of what disjoint means is that they have no outcomes in common, or they cannot happen at the same time. This is also called mutually exclusive. If you've ever heard the phrase mutually exclusive, that means absolutely cannot happen simultaneously. For example, you cannot enroll in a Monday, Wednesday, Friday, 10 o'clock morning class and also enroll in a Monday, Wednesday, Friday, 10 o'clock morning biology class, right? Like you can't be two places at once. So that's what mutually exclusive means. If you want to look at the Venn diagram, it's probably been a while since you've seen these. Do y'all remember Venn diagrams? The rectangle is your universal set, everything you're studying. And then inside these little subgroups, I'm going to name them E and F. And you'll notice that the circles don't overlap, meaning it's impossible for them to happen at the same time. So event E could be like being a dog, and event F is being a cat. Well, you can't be a cat and a dog at the same time. I think there's an old cartoon called Cat Dog, but that's totally an exception and definitely not the rule. So what if I wanted to know, well, what we did before is, what's the probability that event E happens? Now I want to know, what's the probability that E or F happens? One or the other, or possibly both, but we can't have a both because they don't overlap. So probability of E or F happening when you have disjoint events is very simple. You just take the probability that E happens and you add it to the probability that F happens. So you take the probability of E and you add it to the probability of F. I mean, that's why this section's called the addition rule, right? Because we're going to add. So when you see the word or, you need to think addition rule. The word or is going to be synonymous with addition rule. Okay. So let's try a real simple example here with a deck of cards. After teaching this class for as many years as I've taught this class, I have come to realize not everybody is familiar with the layout of a deck of cards. So this is the layout of a deck of cards. The first thing you need to know is that there are 52 total cards. And they're in like 4 groups. So you have an ace, 2 through 10, and a jack, queen, king. And there's like 4 rows of them. So what you have here are the clubs. You have the spades. This is describing the shape on them. You have hearts. And you have diamonds. I don't think students mess up heart and diamond, but they tend to confuse clubs and spades. If you've ever used a spade-tipped shovel, it's called a spade because it looks like a spade. I'm not trying to be sarcastic. It's just that's what it's called. These are called the face cards because they have faces on them, and your textbook sometimes calls them the court, like the king's court, right? Like the royalty. Okay, so that would be the face cards. The ace, for all of our purposes in this class, it's going to be equal to 1. I know in different games it can have different values, but it's just going to be a 1. We're not going to make this hard. Okay, so with this basic layout, 52 total cards. Oh, and half of them are black and half are red. If you didn't print your notes in color, you want to make a note that the top 2 rows are black, the bottom 2 are red. I want to know, first of all, just a simple, what's the probability that we draw a jack? How many jacks are there out of the total number of cards? How many ways could you get a jack? Well, there are 4. I'm going to circle it on here. There's 4 jacks. So when you draw that card, any of those 4 would work. So 4 out of 52. And let's just do fractions here. Let's reduce that. 4 out of 52. Oops, I forgot to reduce it. There we go. 1/13. And actually that reduction makes sense because there's 13 cards in each one of these suits. These are called suits. So 1 out of every 13 is a jack. 1 in each row is a jack, so that's why it reduces. Now I want to know, what's the probability I draw a jack or a 5? And when you see that or, you're like, oh, I know what's going to happen. I'm going to have to add. jack, or a 5. Now, when I draw the little bubbles around here, do you see that my bubbles didn't overlap? That's because you cannot have a card that has a jack and a 5 on it at the same time. It's not possible. They're disjoint. And you can see when you draw the bubbles, it's disjoint. So getting a 5 or getting a jack, well, there's 8 cards. You add them together. So it would be 8 out of 52. You don't actually have to work out a formula. You just have to count. There's 8. And 8 out of 52 as a fraction is 2/13. Think about it. 2 out of every 13 cards is either a 5 or a jack. Now we're going to go one more step. What's the probability I draw a jack or a 5 or an ace? Well, all those ors mean you're going to add. So aces also disjoint from the 5s and the jacks. See, no overlap. So there's 4 of these, 4 of these, 4 of these. That would be 12 out of 52. So if you just would like print out the picture of the deck of cards and then draw on it, I think that's going to be the easiest way to go about these. 3 out of 13. 3 out of every 13 cards is either an ace or a 5 or a jack. So it's real simple in the disjoint case. Let's try one more where they're disjoint. I went all out on the clip art here. I know you're super impressed. A bag contains 5 red marbles. Again, if you didn't put your print your notes in color, you wouldn't see these colors. So these top 5 are red. These 3 in the middle are blue, and then there's 2 that are yellow. So 5 red, 3 blue, 2 yellow. And that gives us a total of 5, 6, 7, 8, 9, 10. 10 total. I did that to make the numbers work out nice. So there's 10 total, and that's the first thing you always want to identify is the total. Like with cards, it's 52, and with this bag of marbles, it's 10. So I want to know, what's the probability if I reach into that bag and I grab one marble randomly? What's the probability that it's red or blue? And these are disjoint because each marble is a solid color. You cannot pick one that's red and blue because each marble only has one color. That's what makes them disjoint. So what's the chance that you get a red one or a blue one? Well, 8 of the marbles are either red or blue. So 8 out of 10, which would be 0.8. That's 80%. What's the probability the marble is red or yellow? Again, or means add. Well, how many are either red or yellow? 7. 7 out of 10. 70%. How about this one? What's the probability that the marble is not yellow? Not yellow means it's not one of those 2. So 8 out of 10. Now that not, that's actually called the complement, and we're going to formally define that in a little bit, but intuitively you already know how to do a complement. Not yellow means red or blue, right? So actually C is asking the same thing as A, just different wording. So those are all disjoint situations. Okay. So now we have to talk about what happens when the 2 circles overlap. So again, I'm going to call this E and F. E and F. Call them E and F, A and B, whatever you want to call them. So there are, you know how in math we do operations, we do adding, subtracting, multiplying, dividing. Well, in the world of Venn diagrams, the operations are intersections, unions, and complements. It's like their language for adding, subtracting, multiplying, dividing. They do different things. An intersection is exactly what you think it is. Think of a street intersection where 2 streets intersect, right? It's right in the middle where they intersect. Well, the intersection is literally the intersection. It's this football looking shape. Okay, that's the intersection. And what's special about points that fall in here is that they are simultaneously landing inside the E circle and also inside the F circle at the same time. So it's this word and. When you see and, it means that both are occurring at the same time. It's an intersection. So and. It's kind of the key word there. And also, you can think of it that way. It falls in E and also it falls in F at the same time. The union is less restrictive, because to be in the intersection, you have to be in both sets at the same time. To be in the union, you just have to show up somewhere. You just have to be in E or in F. Or you could be in the middle. I mean, it doesn't matter. You just have to show up somewhere in one of the circles. So a union is like a coming together of two things. Like, you know, they call marriage a union. Two people, right? So the union would look like that if you shade it. You can see that the shading is very different. Are these points in E or F? Yes. Are these points over here in E or F? Yes. These points in the middle, are they in E or F? Yes. It's just a yes or no question. So it's E or F, or possibly both, because the points in the middle, they fall in one or the other, or both. Now here's the issue that we have. When the circles overlap, let's say this left circle was all the people that had a sister, and the right circle was all the people that had a brother. There are people that have a sister and a brother. So if you count up all the people with sisters and then add them to all the people with brothers, what would happen to those people in the middle? They would get double counted, and it would throw off all your numbers. So there has to be a way that we can do this where we don't double count. And that's sort of the theme for this section, is don't double count. So when finding the probability that E or F occurs, you have to do it in such a way that no one gets counted more than once. So now we've reached the general addition rule. You need to know the general addition rule. You don't have to memorize the formula. I'm going to teach it to you how to do it without the formula, just intuitively. I think that's a better way to go. Because when you leave the class, you may not remember a formula, but if you learned it intuitively, you might remember that. So let's say that this is E and this is F, okay? If I take the probability that E happens, so I take all of circle E, and then I add that to the probability that F happens, you're going to see what happens here. I just double shaded everything in the center, everything in the intersection. So if you do that, probability of E plus F, like we did before when they were disjoint, what you're going to have to do is subtract out an intersection. It's like I painted E, I painted F, and now I have two coats of paint in the middle, but only one on the sides. I just want one layer of paint. So you've got to peel away one layer in the middle. I don't actually know how you would do that, but that's the concept here. We want one flat layer of paint all the way across. So you add them and then you subtract out the intersection. That's the general addition rule. Sounds complicated. It's actually not quite as complicated as it sounds. So we're going to go and do a couple examples to illustrate the addition rule, the general addition rule, when your events are not disjoint.